All right, now we're moving on to something that might be a review for some of you from Chem 200 who may have done Chapter 6. So this is some of the Chapter 6 material in thermochemistry. This first plate is just to remind us of some of the different ways that energy can be found, or what forms energy can be found in. You've looked at light energy in Chem 200, specifically, or for example, you looked at electron transitions in the atom and saw how they absorbed energy in the form of light and gave off energy, and that kind of gave clues to the model of the atom. The electrical energy, we're going to do a whole chapter of that coming up right after this thermodynamics chapter. But in the thermochemistry and thermodynamics, the forms of energy that we most often concentrate on are heat energy and kinetic and potential energy. So I just wanted to kick around those two types of energy a little bit to refresh your memory on what they are and what forms they take. So you may have seen this in physics, the equations for potential energy and kinetic energy. So potential energy has this height criterion mixed into it, and it's often calculated from the mass of some object like a ball, the acceleration due to gravity, 9.8 meters per second squared, and the height it is from some surface. And so you can calculate the potential energy that that ball has. Now, if I let the ball go and it starts dropping, then that potential energy decreases because the height decreases, and the energy gets transferred into what's called kinetic energy, or the energy of motion. And the energy of motion equation is down here, and that's found equal to 1/2 the mass of the object times its velocity squared. All right, so moving right along, this next plate further cements that both of these forms of energy are in fact energy, and they have the same units, which is joules. So I have kinetic energy equation here. I just put in a 2-kilogram object moving at 2 meters per second, and I calculated its energy in joules because I know that a joule is equal to a Newton meter, a force through a distance, and a Newton is a kilogram meter per second squared. So a joule is a kilogram meter squared per second squared. And that's what I have here on the left. And then I can do the same thing with the potential energy equation, plug in just some numbers just to show you how the units work out again to joules. Also, we're going to have to sometimes convert joules to calories. So we know our conversion factor, and we know that those calories they're different from the calories that you might see on your package of Twinkies or whatever you're eating. Those are actually kilocalories, and they signify that by putting sometimes a big C instead of a little c. All right, now on to thermochemistry. Now, we want to be able to track energy and how it changes from one form to another during a chemical reaction. So one of the things that's often done is to define places where energy can exist. And so the most simplest definition of the many possibilities of of defining these places where energy can exist is just to break it down into two locations. One we call the system, and that's usually the thing that we're focusing on. For chemists, that would be some chemical reaction. And then everything that's not a part of that chemical reaction is called the surroundings. And then the two of these things make up the universe. So you can think of this way of dissecting areas where energy can exist to be comprehensive. And if the surroundings include everything in the universe, then you can see that later on, when you go back to study this for some other problem or project, that if you want, you can start to dissect the surroundings. For example, if I have an explosion in a room, um, or instead of doing it in a room, let's do it in a styrofoam cup. And you may have done something like this in a physics lab, where you put in a heated metal into a styrofoam cup and water's in there. So your system would be that hot metal, not and how that metal got hot, it could have been an explosion or whatever. But anyway, that you can define as your system. And then the system, that hot metal, once it goes into the water in the styrofoam cup, um, can give off heat. And so energy can come from that system into the water, and we can define that water as the surroundings, right? And that would be the universe. But say, oh, well, there's some leaking from the water into the styrofoam. So then you need a heat capacity of the styrofoam, and further dissect the surroundings to water in the cup. But then say you want to continue that and say, well, maybe there's some energy that leaks from the cup into the room. And then you can, dissect that again and just keep adding on more terms of where energy can exist. So when we first study this, we try to make it as simple as possible and just say, the system is the thing that we're going to focus on. Everything else, the surroundings, we'll call it, and that, you know, makes up the universe. But that can be subdivided in a perturbation type of a technique where each term um, might have a smaller and smaller amount. So it just depends on what precision you want to do your analysis at. If you want to make it more precise, then you might have to add in more places where energy can exist. But I think you get the idea. We're just going to look at it very simply here, but it's easy to split it up into more if you have to later. All right. Let's see what we got. Next plate talks about a couple forms of energy called work and heat. You recognize work probably from physics as a force through a distance. And you know that the units come out for that as joules, because it's a Newton times a meter. And heat is maybe a little different to get an understanding of, but again, you may have done these uh, experiments either in chemistry or physics where you looked at heat and its transfer. You know that heat always flows from a hot spot into a colder spot. And you may have seen an equation like this for calculating the amount of heat that's transferred in this situation of where you have a hot body connected to a cooler body. So that amount of heat is measured from the mass of that object and the change in temperature that it experiences, multiplied by this proportionality factor, which we give the symbol as of S, or specific heat. Can anybody guess what the units of specific heat would need to be, in order to get, say, Q, in units of joules, maybe? Anybody want to guess the units of specific heat? Are you guys still on spring break?
I'm trying hard to remember them, but I can't.
Good, because this is a situation where you don't have to remember anything. And I'm going to show you how to do this. Give me a unit of mass for the M.
Grams,
Sure. Okay, give me a unit of temperature.
Celsius.
degrees Celsius.
Yeah, cool. All right, so now I know that I need Q in joules. So what's the units of S have to be? Well, it has to have joules on the top, right?
Would it be joules over grams degrees Celsius?
Yes, indeed. Very good. So that's the typical unit of a specific heat. And it's a proportionality constant, just like R was for the ideal gas law. You know, and other proportionality constants that you guys are going to run across. And that's just says keeping all things constant except the mass and the change in temperature that it experiences. This object, whatever it is, you can't change it. It could be gold, then that has a specific heat. If you change it to silver, then that's a different specific heat. So it's specific to that object. It's just a proportionality constant. As long as you keep that object as it is in its form, then there's a number that's specific to that object and how it absorbs heat or how it gives it off. And the amount that it gives off is dependent on the mass of the object and the change in the temperature that it experiences. But as long as that object stays the same, it always has the same specific heat. For example, the specific heat of water is 1 calorie per gram degree Celsius. So that's S for H2O. All right. And for in joules, anybody know what the specific heat of water in joules would be?
Is it 4.18?
Yeah. Yep. It's the conversion between calories and joules. I think we mentioned it back here somewhere. Yep. There it is. And you are correct. So 4.18 joules per gram degree Celsius. So it's not a mystery or anything. This will help you calculate any heat flow for those situations that we talked about, a hot to a cold transfer. All right, moving right along in our thermochemistry, we get to the first law of thermodynamics, which is pretty much a law for accounting. And maybe that's why a lot of chemists, if they don't find a career in chemistry, they become an accountant. But anyway, this helps you keep track of the energy, and what it says is that energy can't disappear. It can flow from one area to another, but it's conserved. That's the first law of thermo. And how that can be shown in a mathematical form is any one of these equations down below here. For example, if energy can't be destroyed and it can't disappear, then the total has to be a constant. So the energy of the universe, for example, equals the energy of the system plus the surroundings, and it has to be some number. It has to be constant. So energy doesn't come in or out of this situation, and we can formulate that law like equation 1. Another way of saying that is that any change in the total energy has to add up to 0. In other words, if 5 joules of energy come out of the system, then they got to go somewhere. It has to go into the surroundings, and the sum of those changes have to be 0. Now, for chemistry, we want to define what's called the internal energy of the system. So this delta E here, sometimes you'll see it with a subscript SYS, and that corresponds to the energy of the system. Now, the changes in that energy are found to be the sum of heat into or out of the system plus the work done by the system or the work done on the system. So this kind of looks like this form of the first law of thermodynamics, but it's applied now to just the system. And it incorporates those two concepts that we just went over, heat and work. All right, so we're going to need to be able to distinguish when Q, the heat flow, is positive and when it's negative. And same thing with work. Okay. All righty. Moving right along. So how can we do that? Well, we can do that fairly easily because of our analogy with heat. When a reaction gives off heat, for example, how do we describe that? What do we say?
Exothermic.
It's exothermic. Oh, okay. So when a reaction gives off heat, we call that exothermic. Now, can we define a quantity that tells us how much heat is given off? Do you remember that from Chem 200?
Wasn't it like the change in something? No, I don't
Yes,
remember.
it is.
Okay.
Delta H. You remember that?
It's coming back.
Yeah, good. So delta H, the change in enthalpy. Now, under certain conditions, namely constant pressure, delta H equals Q, and we put a little P there to signify that Q is under constant pressure conditions and therefore equals delta H, the change in the enthalpy. All right. So I think now with this analogy, it's easy to figure out whether delta H is exo or endothermic, and therefore whether Q is positive or negative. So when a system, like a chemical reaction, when it gives off heat, we call that exothermic. And so the sign for exothermic delta H is positive or negative?
Negative.
Correct. And so Q is negative. So when Q is negative, less than 0, heat is transferred from the system to the surroundings, right? And whatever the surroundings is, usually for a chemical reaction, that would be water, the temperature of the water increases. So we see that heat given off as a rise in temperature, and we call that exothermic. So Q is negative. When Q is positive, heat is absorbed into the system, and delta H is plus. So by analogy, I think with something you already know, you can figure out the signs for heat into or out of the system, just like delta H. Because under certain conditions of constant pressure, delta H equals Q. All right, now once you rationalize that, then it's easy for work, because work's the same way. When the system does work, it gives work, that W is negative. When something does work on the system, then the work is positive. Okay, so that's what these guys say down here. So if you can remember the comparison to delta H, which you already have a pretty good idea how that works, exo and endothermic, then it's an easy step to rationalize the sign of Q, and then W follows in line. Any questions on that? Okay. Oops. Now, some other properties we're going to have to remember or learn, and that is the property of being a state function. It turns out that energy or internal energy of a system, like a reaction, is independent of how it got there. It just depends on what state it is at that point in time. You know, is it liquid, solid, gas? How many moles of whatever it is exists, so forth. What is the state? What's the temperature of that thing? What's its pressure, and so forth? I don't care anything about its history. So what does that mean? Well, that means that the energy of 50 grams of water at 25 degrees is some value. And that value does not matter whether I created that energy from 50 grams of ice and I let it melt, or I took 50 grams of boiling water and let it cool. I don't care about its history. I just care about what state it is at that point in time. That type of property is called a state function, and internal energy is one of those. So what does that mean? What's the consequence of being a state function? That means that if I want to find the change of energy that occurred when something went from one state to another, then I can just find their energies at those 2 points and subtract them. I don't care about the path in between those 2 points. And so that's the advantage of being a state function. Some things that are not state functions are heat, flow, and work. They're not state functions, they are path dependent. For example, I have this ball A, it's going to come down this surface and it's going to strike ball B, and it's going to give energy to that ball B. The amount of heat that is given off when A goes down to hit B is path dependent. In other words, is this path here smooth, or is there a lot of bumps on it? Because if there's a lot of bumps, heat's going to be given off here, and this path is going to heat up, and it's not going to hit ball B with as much kinetic energy, and so it's not going to do as much work on ball B. So heat flow and work in general are not state functions. They're path dependent. If it's a smooth path, frictionless, then less heat's going to be given off, as opposed to if it's very bumpy. All right. But notice over here that the internal energy is not. So the internal energy of A had something here, some potential energy. And then it goes down to here, which is 0. Then I can calculate that delta E, the internal energy, would be 0 subtracted from whatever it was, and that would be the change in the energy of A. So that is not, that is a state function. That's not path dependent. It only depends on where it started at and where it finishes. Okay, so now we go back to some of the things that you looked at in Chem 200. Since this is a state, internal energy is a state function, I can find changes in it by just looking at the energy of the 2 points. We remember our exo and endothermic definitions and how that is experienced as far as the surroundings. In an endothermic reaction, heat's absorbed, so the surroundings get colder. In an exothermic reaction, heat's given off, so the surroundings get hot. This is something we kind of alluded to before, how enthalpy is related to Q, but it has to be under constant pressure conditions. So in fact, they are equal to each other in those constant pressure conditions. And we can use those analogies that we talked about before. When delta H is positive, Q of the system is positive. And when delta H is negative, Q of the system is negative. Note that the change in enthalpy is a state function, just like the internal energy, even though it's made up of 2 functions, heat and work, that aren't necessarily state functions. Q is under certain conditions, but not in general. All right, this slide shows some of the properties of enthalpy. It says for this first slide that this first line anyway, says that enthalpy is an extensive property. So what does that mean? Extensive means the amount. So it's amount dependent. How much does it extend? So if I have some reaction, this first reaction of methane, and I'm going to explode or combust methane. I'm going to form CO2 and some water. And I know that when there's 1 mole of methane, I get 890 kilojoules of energy released into the surroundings. If I double the amount of methane that I burn, then I'm going to get double the amount of heat that's given off. So that's what it's meant to be, an extensive property. It's just amount dependent, and those stoichiometric coefficients come into play for those type of properties. All right, what's this next property show down here? It shows that enthalpy is a state function. Remember, it just matters what state it's in. That's the energy content that you get. So if I have a reaction that produces liquid water, I'm going to get a certain amount of energy out from that reaction, as opposed to a reaction that produces gas. That's a different state, and it's state dependent. So I'm going to ask you guys, which one do you think has more energy content? 2 moles of liquid water or 2 moles of gaseous water? Which has more energy?
Would it be the gaseous water?
Yes, that's what I would say too, right? Because it takes more energy to give to the water to break the intermolecular bonds in liquid water to make it gaseous. So this guy has more water, so more energy, the gas, and so it gives off less energy to the surroundings. So that makes sense, right? Oh, I hope it makes sense.
Yes, it does.
Okay, good. Now the last one is when a reaction is reversed, the sign of the delta H for that reaction changes. Okay. And so a way to see this, I think, let's put in a slide here. Let's just take some reactions. So I have, let me get rid of this thing. Okay. Sorry about that. Go away. All right. So say I have some reaction, and here's the energy, and this is the reaction coordinate as the reaction proceeds from some reactants through a transition state to some products. Okay. So here's my reactants and here's my products. And the delta H is here. Okay. Now, let's say instead I start out with the products here and I go through a transition state and end up with the reactants here. Again, the delta H is this sign, but you see final minus initial in this scenario is going to be plus, final minus initial in this scenario is going to be negative because this is less. But these amounts, this distance is the same as this distance over here. It's just the sign that's different. Okay. So that's what this is saying. when you reverse a reaction or consider the products as reactants and the reactants as products, then the delta H is not the same, but it's related. And it's related by an inverse sign. All right, any questions on that? Okay, now, the thing that we've been trying to get at by looking at these properties and showing that they're state functions and that they're extensive and so forth is because we want to introduce a way to calculate these thermodynamic properties like delta H for a reaction without having to go to the laboratory to do any experiments, right? Because you could go to the laboratory and take a couple reactants, react them, and see, for example, uh, if energy is given off in the form of heat or it's absorbed, and we can see how much by, say, the change in the temperature of the surroundings, use its specific heat and its mass. But instead of doing that, we want to know, is there a theoretical way to calculate this without having to go to the laboratory every time? And you probably guessed it. Yeah, there is a way. And a way to do that is to use Hess's law, which we're going to look at, and you may have seen that in Chem 200, Hess's law, along with this idea or this concept of delta H of formation. And together, these two concepts will allow us to theoretically calculate the delta H of any reaction by just looking up tabulated values. Okay, any questions so far? All right, so we got to see what Hess's law is and the delta H of formation. So let's start off with Hess's law. Hess's law says, kind of in, I think, simple terms, is that, say, you have this reaction and you want to find the delta H for it, and you don't have it. But you have the delta H for one other reaction and the delta H for another reaction. And when you add up those reactions, they equal the one that you want, then you can add up their delta H's. That's what Hess's law says. For example, we have this reaction 1. Well, first of all, we want to know what the delta H of this reaction is, and we don't know it. Okay, say we don't know that. But I know the delta H of reaction 1 and 2. And when I add up these two reactions, then I get the reaction that I want. Then Hess's law says all I have to do is add up their delta H's, and that value equals the reaction that I want. Any questions on that? So Hess's law is, I think, pretty straightforward. This is a picture of Hess's law, maybe to give you an idea of what's going on. It's kind of doesn't come out too well on my computer, but anyway, this is methane here, and I'm gonna combust it to form CO2 and water. And I want to know its delta H of combustion, but I don't have this value. But I have this value for this step, and then I have another value for a further step, so I can add these pieces up. And you can see that when you add these pieces up, you get the piece that you want. That's pretty much Hess's law in picture form. Okay. Now we move on to the next concept that's going to allow us to calculate delta H's of any reaction without having to go to the lab. And that's the idea of this delta H of formation. Now let's read the definition of this. When 1 mole of a compound is formed from its constituent elements, the enthalpy change for the reaction is called enthalpy of formation, and it's given this term right here, delta H with a little subscript F and a superscript 0. Now the superscript 0 is our condition terms. It's under standard conditions. That's what the superscript 0 signifies. So standard conditions for reactions are when gases are at 1 atmosphere, if there are any gases, and that the whole system is at 25 degrees Celsius. So that's standard conditions. And I have to form 1 mole of this compound from its constituent elements under standard conditions. So for an example, say I want to form water. Okay, so I want to form water, H2O. So what are the elements that I would need to form water? Anybody know?
Hydrogen and oxygen.
Good. So I need hydrogen and oxygen. Now, what form do they exist under standard conditions? How does hydrogen exist?
I think it's a gas.
Gas?
Yes. So it's H2, and it's a gas, and it's a homonuclear diatomic, right? Okay. And how about oxygen?
That's a gas too.
Yeah, it's another homonuclear diatomic. It's not only a gas, but it's homonuclear. So these are what's defined as the constituent elements. That's how those elements exist under standard conditions. Now, if I wanted to balance this, I could, right? I could put a 2 here and a 2 here, and then it would be balanced. Now, does the delta H of this reaction equal the delta H of formation of water? The answer is no, it doesn't. Why? Because the definition is for 1 mole, and this reaction has 2 moles. So the delta H of this reaction actually equals 2 times the delta H of formation of water. Any questions on that? All right. So what happens when some compound or some element has 3 different forms, like carbon does? This element, which one are you going to use? Which one is the standard? So when an element under standard condition has more than one way to exist, what they do is they take the one with the least amount of energy and assign that to be 0, right? And so graphite has the least amount of energy as far as carbon is concerned compared to diamond or its gas form, which is C60. It's called buckyballs or Buckmiller fullerenes. Anyway, that's another form of carbon, but it's got the highest energy of them all. So we take the lowest form and assign that to be 0, just like we assign all elements in their standard conditions to have delta H of formations as 0. They're defined as 0. Now, what does that do? That gives us a point of reference. We don't have to form the elements in their standard conditions because this is the way they already exist. They're already formed. So it doesn't take any energy and it doesn't give any energy. That's why we can define it as 0. But it gives us a reference. And we can use that reference to calculate the differences in energy for any reaction, and therefore their delta H of reactions. And so I use this analogy here to try to help you understand this concept. Now, let's pretend that we wanted to find the difference in our heights. I could measure myself from the floor to the top of my head, and so could you, and we would take the difference, and that would give us the difference in our height. But say, like enthalpy, it's really hard to measure that. You can measure the enthalpy for water, but it's very hard because you have to take into consideration all the repulsive forces between the protons of all the atoms in there with the protons of all the other atoms, as well as the repulsive forces of all the electrons flying around in that molecule against all the other electrons. Plus, you have to incorporate all the attractive forces between shared electrons and other protons and things like that. It's just a very complicated problem. So instead of doing that, we measure relative to something that we've defined as a 0. For example, we could measure our heights, say, to some other reference, like the middle of the Earth. I measure my height to the middle, you measure your height to the middle, and then we take the difference between those two values. That gives us what we want, which is the difference in our heights. And it's the same thing with enthalpy, except enthalpy is a lot harder to measure absolute enthalpies. Our absolute height's easy to measure. We could just, get a tape measure out from our toe to our head. But what we're doing, instead of picking the center of the Earth for our heights, we're picking the elements in the periodic table under standard conditions as they exist. We're picking that as the 0. And then we're measuring the difference in enthalpy from that reference to what other to other molecules that we might want to calculate the change in the enthalpy of. So I don't know if that helps or not, but maybe, taking a look at this in a couple more different ways will help you understand what's going on. All right. Now, what laboratories have done is all over the world, they have tabulated these delta H of formations that they found experimentally. So here they took graphite and hydrogen and they formed this molecule, and they found that for 1 mole of that molecule formed, that's how much energy was given off. So its delta H of formation is that value. And they tabulated all of these delta H of formations. This is just a subset. Your textbook has a huge pages, lots of pages of delta H of formations. Online, lots of pages of delta H of formations. So now once you have these delta H of formations, you can use those in conjunction with Hess's law to calculate the delta H of reaction of any reaction that involves these molecules. Okay, so let's see. Here's a nice picture that attempts to explain what's going on here. All right, I have this reaction of propane, and I'm going to combust propane with oxygen. Okay, these are my reactants. So I want this delta H because I'm going to combust it and I'm going to form CO2 and water. But I don't want to go to the lab and get this number. Is there a way to get that value using Hess's law and this idea of delta H of formation? Yes, there is. Okay, instead of taking methane in a direct route from the reactants in oxygen and getting these products, what I can do is I can take methane and theoretically break it up into its constituent elements, which is graphite, hydrogen, and then these oxygens were there already. Okay. So this first step is the opposite of the formation of propane. So I can look this up for the first step. This is going to equal minus the delta H of formation of propane. So I can look this up in your textbook. I don't have to go to the lab. And now I have propane in all its constituent elements. And now I can start forming the products over here. I can form my 3 CO2 molecules, and I can look this up in your textbook. And then I could go ahead and form my water in the next step. And I can look this up. And I could notice that in the book, it's for 1 mole of water, but all I got to do is multiply that by 4 because it's an extensive property. All I got to do over here is multiply the delta H of formation of CO2 by 3, and I get that value. And then Hess's law says, all I need to do is add up all these steps, 1, 2, 3, to get the step that I want, which is the delta H of the reaction of the combustion of propane in oxygen to form CO2 and water. Does anyone have any questions on how you use this idea of delta H of formation along with Hess's law to calculate the delta H of any reaction? You're going to probably have to go back and think about it and study it a little bit, go over the definitions, I would think, in order for it to cement. You're going to have to probably sleep on it a little bit too. But I hope that's clear. I hope you can go back and study this and be able to logic your way through, because I think it's interesting. It's an interesting way to put two concepts together and use those concepts to calculate something like the delta H of a reaction without even having to go to lab, just using tabulated values of this idea, delta H of formation, where everybody uses the same reference. And that same reference is the elements under standard conditions in the way that they already exist. And you define their delta H of formation as 0. So you're just defining that as your reference point and then going from there. Any questions or comments? All right. Now, having said that, I think it's really neat and important to understand how to do or how to reason through that logic. But as far as, calculating delta H of reactions, it's a lot simpler. You don't have to understand that logic. You just have to understand this equation and plug in those values. For example, this equation here tells us how to calculate the delta H of any reaction under standard conditions. That's what that's 0. By using the delta H of formations that are published in your textbook or online. Now, all you need to do is take the delta H of formations of the products minus the reactants. Because delta H is a state function, I can take final minus initial. Also, because delta H is an extensive property, I can multiply these values by the stoichiometric coefficients because it's amount dependent. It's extensive. And I do that for all of the products. So that's what this sum sign means. I add them all up for the products, and I add them all up for the reactants, and I just subtract the two. And the difference between those two is going to give me the delta H of the reaction. So all of that theory and all of those ideas, the result is this equation for calculating the delta H of reaction. Any questions on that? Okay, so once you understand that equation, it's really easy to apply. And in the next plate, I have an example of its application. So here's the example of propane reacting with oxygen to form CO2 and water. Now notice that this is liquid water. So when I go to look up the delta H of formation of my products, I have to make sure I pick out the right one from the tabulated values. But if you apply that equation, then you should be in good shape. So I start with my products first. So I have 3 CO2. So 3 times the delta H of formation of CO2 plus 4 times the delta H of formation of liquid water minus 1 times the delta H of formation of propane minus 5 times the delta H of formation of oxygen gas. Now, if I go try to look up the delta H of formation of oxygen gas, I'm not going to find it in my textbook, and I'm not going to find it online. Does anybody know why? What is the delta H of formation of oxygen gas? Well, it's an element in its constituent form under standard conditions. So what's its delta H of formation? Anybody? It's defined as 0. Remember, that's our reference. Any element in its standard form in standard conditions, right? How about the delta H of formation under standard conditions of copper metal? Anybody know what that is?
Would it also be 0?
Yes. Right? So you have to look at the periodic table. And if you see the periodic table, sometimes they're color coded, and the ones that are in black signify solids. So copper is a solid under standard conditions. So its delta H of formation is 0. How about the delta H of formation of helium gas. Zero, right? And so forth. So, you know, don't forget those guys. They are, by definition, because of the way we defined the delta H of formation back here. Where is it? Maybe we didn't define it. Maybe we should define it. Yeah, I kind of gloss over it back here in the notes. I should probably say this more explicitly. It's kind of hinted towards here for carbon, since graphite has the least amount of energy compared to the others. We define that one as zero, but all the other guys that exist in their standard states also are defined to have a delta H of formation of zero when it's in the elemental form. Because you don't have to form them, they already exist that way. Okay, so that would be an important concept that I think I should probably write out and not gloss over. We did say it over here for these guys, but I think I should probably say more on that. Any questions on that? So all the elements in their standard states and conditions have a delta H of formation of zero because that's the way they naturally occur. You don't need to put in or take out any energy. They're already that way. So it seems like a appropriate reference point. Now, if we said they have total energy, that would be wrong. We're just saying they have this delta H of formation to be zero. That doesn't mean they have a total energy of zero. So in our analogy for heights, if we wanted to measure our heights and we picked the same reference, like the same desktop, and I measured my height from that desktop to my head, you measured your height from that desktop to your head, and we took the differences because that desktop was defined as the zero, then our difference between those two numbers would be, in fact, the difference in our height. We don't have to measure our total height. And so what we're doing is we're taking the elements in their standard states, since they're already formed, and defining that as a delta H of formation of zero. Okay. Any questions on that? So that's thermochemistry. And next time we're going to go on to thermodynamics. I want to stop there. And if anybody